Good morning, everyone. Today we are going to continue our talk about phase diagrams. Today's objectives include, and we want to learn how to compute the relative amounts of primary and eutectic microconstituents, and we want to learn terminal solid solution, intermediate solid solution, along with intermetallic compounds. And we also will learn eutectoid and peritectic reactions. And then we will learn congruent transformations. And please note there are several important concepts. We have learned eutectic. Today we are going to learn eutectoid, peritectic, and congruent transformations. I want you guys to know these four basic concepts very, very well, very, very clearly. Whenever people ask you the questions, you should be able to tell people the distinct differences among all these different concepts. First, we talk about computations for relative amounts of primary and eutectic microconstituents. And we still use this lead, tin, and phase diagram as an example. This is in computations for relative amount of primary, alpha, and eutectic microconstituents. So we still have used this is a phase diagram. This is here's alpha, here's a beta, here's L, alpha plus L, beta plus L, and this area is alpha plus beta. Questions so far? So also this is the abscissor is the combination of tin, and this ordinate is the temperature. And this slide shows computations for relative amounts of primary and eutectic microconstituents. So first equation, the level rule is said we use the level rule. WE equals WL equals P plus L. Okay, so this is the uh, W alpha prime equals Q and P plus Q. A level rule expression for computation of total alpha phase mass fraction. And for this mass fraction, and this is total, and total will be this denominator will be P plus Q plus R, numerator will be Q plus R. So level rule expression for computation of total beta phase mass fraction, and we use this one. Use this equation. Please be very, very careful. And during the quizzes or the exams, you need to be very, very clear what the questions ask about. And then you can select the appropriate equations to solve the problem. And please note that all the quizzes and this is exams will be take-home exam or take-home quizzes. That means you do not need to memorize these equations. However, you need to have clear understanding of each of these equations. Otherwise, and you cannot compute. And this is a fraction, this percentage very, very well. I need to remind you very, very clearly. Okay, understanding is the key to solving all these problems correctly. And then we talk about equilibrium diagrams having intermediate phases or compounds. So this is very, very interesting. And we just talk about the phase diagram of lead and tin and also copper and um, for the brass we have copper and uh, we have copper and also another component you should know that the for these two phase diagrams we do not have intermediate phases or compounds. Intermediate phases means that and so this is either for these previously and and copper and thin copper for this is a brass component a brass the the metal alloy. And so it is easy either this is the first component or the second component. And for this is lead and this lead tin phase diagram, either lead or either tin, and there are no intermediate phases or compounds. But for this equation, for this diagram, and things are different. You can see how complicated this phase diagram is. This corp zinc, this phase diagram, this corp zinc phase diagram. And so this is this is alpha, this is liquid, alpha plus L, beta plus L. So this gamma plus L, delta plus L, and epsilon plus L. Here is the this is eta, okay? So this is eta, here this area, I'm sorry, this is a very small area, and you can see it's a small area, eta plus L, and here is the eta. This is alpha, and this is eta. So you can see so many different the phase fields, and it is very complicated material. And any questions so far? Okay, so these are having intermediate phases or compounds, and this is some compounds here. Okay, so these are some uh, so terminal solid solutions and exist over carbonation range near the concentration extremes of the phase diagram, the terminal solid solution. Intermediate solid solution phases found at other than the carbonation extremes. So intermetallic compounds. So these intermetallic compounds. Here is the intermetallic compounds, and you can see this diagram. This is magnesium, and this is lead. So here is the temperature, and you can see alpha. We have a beta here, beta plus L. This alpha plus L. So here is L. So here is this is L plus magnesium and lead. This Mg2 Pb. So this one, okay, when this is the Pb's carbonation equals 80%, and we will have a compound. And please know that this compound is a new material. Be careful. It's new material. This compound is not magnesium, is not lead. It is new material. So exactly when the composition equals this one, when the composition equals 80, around 80, a little bit higher than 80, so we can get these intermetallic compounds. You should be very know that sometimes when these two materials come together, they cannot they can not just become a solid solution. Instead, they become a new material. So this is called intermetallic compound. And so then we intermetallic compound for some systems, discrete intermetallic compounds rather than solid solutions may be found on the phase diagram, and these compounds have distinct chemical formulas. And this is what I just told. Note, intermetallic compound exists as a line on the diagram. This I show you a line, okay? Only when this combination equals precisely equals this combination, and we have a compound. Not of area, because of stoichiometry. Stoichiometry is the combination of a compound is a fixed value. Right? So this is be very careful about these intermetallic compounds. And then we talk about eutectic, eutectoid, and peritectic. Eutectic reaction, we know that it is from a liquid, and we cool it. We have two solid two solids, alpha plus beta. Then if at this point, if we heat alpha and beta, we can get this is liquid. So this is called eutectic. And for this lead and tin phase diagram, and we know the temperature equal the eutectic temperature equals 183 degrees C, and also the Thin's coordination is 61.9 with percent. And the new one, the new reaction is called eutectoid. Okay, eutectoid is different. How different it is? It is um, one solid phase transforms to two other solid phases. For example, S2 equals S1 plus S3. So this is a cooling and this is a heating. And so here, for example, this is a gamma phase. If we cool it, we have this alpha iron and plus this is the compound. And we have, for example, for this iron and carbon phase diagram, at this temperature and with this combination of this carbon, and we will have this eutectoid reaction, and it is um, gamma iron, alpha iron. So this is a intermetallic compound. Also, this is cooling and this is heating. And the third one is peritectic, liquid and one solid phase transform to a second solid phase. And solid liquid equals another solid. And for this is a air and carbon phase diagram at this temperature, it's very, very high temperature. With this combination, we will have peritectic, uh, peritectic reaction. Solid liquid equals another solid. Questions regarding this slide? Okay, I want you guys to learn um, these three different types of reactions and also know what they are talking about and how they are different from each other. And you should know that this is so these reactions are associated with specific temperature and specific this combination. And so here eutectoid and peritectic. This is a copper. This is the copper Xeon on phase diagram. And so here, okay, so look at it here. Um, Composition, this is temperature, and here, and can somebody tell me which point is eutectoid, which point is peritectic? And before I show you, I want you um, to tell me, in this phase diagram, and which point is eutectoid, which point is peritectic. First, you should know what is eutectoid. Eutectoid, what is it? We just talked about eutectoid, right? So this is eutectoid means that, and here is one solid, and then we will have, and this is two other solids. And peritectic, we have, and this is solid, and we have, and this is we have, this is a solid, plus this is a liquid. We have another solid. Okay, we can see here. So this is eutectoid phases. Okay, and so if we lower temperature, delta become gamma plus E. So this is eutectoid the reaction. So here peritectic transformation and gamma plus L equals another through another solid. So this is this point. And then we talk about congruent phase transformations. Phase transformations for which there are no coordination alteration, the congruent, as the name suggests. For example, allotropic transformation, right? Allotropic transformation. You know allotropic transformation, right? So there's no coordinational alteration. So in congruent transformation, at least uh, one of the phases will experience a change in coordination, e.g., um, eutectic and eutectoid as well as a melting of alloy that belongs to isomorphous system. So here is the VMSE, this interactive phase diagram. And so you can see, you can use this one. Okay, so here is a phase diagram, this coordination, this alpha, liquid plus alpha, and you can select any point, and then you can get, this is you can get select any point, and then you can get um, the phases present on. Also you can use the draw a timeline to calculate the combination and of different phases, and also calculate the weight fraction with the percentage um, of this is the different um, the phases. Okay guys, so today's lecture is short, but and it's very important. I want you guys to know the several important concepts. What is a eutectic? What is a eutectoid? What is a peritectic reaction? And also what is a congruent reaction? And I hope you guys, um, if I give you a phase diagram, I hope and you guys can tell me which point is eutectic and which point is eutectoid, which point is peritectic, and which point is congruent. And uh, they are different. Okay, I need to also tell you that not each of these phase diagram has all of these four reactions. Be very careful.